Right, so I guess let's start. So before we go on to the lesson, just a few remarks regarding homework and textbook and all that stuff. So first, when you look at homework, right, there are the hand-in assignments and the homework. And a few of you asked me what's the difference. So you have homework 1 through 6. Those homework are do-it-yourself practice problems. You have solutions to them. But don't be tempted to look at the solutions. Here you see solutions. So far, only solutions to the homework are posted. I will also post solutions to the hand-in assignments. Right now the folder is empty because you haven't yet submitted any assignments. You understand that when you go through this course, you should try to solve a few problems. You should look over the homework problems. You should solve it yourselves and compare the solution to what I posted. Then ask me questions if you need. Another thing is, speaking of office hours, again, I usually don't come early unless you ask me to come early. So if you want to see me, you just send me an email the day before and I'll come and see you. Good? Now, the hand-in assignments. Let's see what's assignment 1. So this, by the time we're done with chapter 1, you should be able to do. So let's say it's due, well, let's say it's due 2 weeks from today. Sounds good? Could be, you can do it much faster, but 2 weeks from today, I will mention when you should submit it. Now,
wait, so it's not due 2 weeks from today?
Yeah, let's say it's due 2 weeks. Again, it's a bit loose. Don't be too scared, right? If you didn't bring it 2 weeks from today, I'm not gonna hunt you. Okay? It's an easy class, easy going. Okay? So another thing, it's mentioned also in the assignments that were, some homework. The homework problems are taken, many of them from Corollary. So Corollary's real analysis, where is it? I feel rather stupid. I'm not sure what's going on. Right? I'm staring at it, but again, Corollary's real analysis, you should be able to find it. Another very good analysis ontology is Stein and Shakarshi. So it finds, again, pretty. Yeah. So you have, those books are independent. You have Fourier analysis, real analysis, complex analysis, and functional analysis. So this is a very good source once you study analysis beyond this course. Good? Any questions? Yep.
I missed the beginning. Did you mention anything about homework?
Yes. So all I said is this. So when you go onto my website, there are going to be 2 links: homework and hand-in assignments. Homework, you have homework 1 through 6. Those have solutions posted on my website. Those are do-it-yourself questions. Okay, so you try to do it on your own, see if you're comfortable with the topics, and then you can check against my solutions. And then you have hand-in assignments, so you see them. Those are the assignments that you hand in. And the first assignment, I said, let's make it do 2 weeks from today. Good? So here is what we finished with last time. We talked about least upper bounds and greatest lower bounds. We spoke about the least upper bound property, and we mentioned that least upper bound property implies the greatest lower bound property. Okay, we proved that in the last lecture. Now, we can try to say a few things about what is R. What are the real numbers? So, if you look into the appendix, I'm not going to cover it in this lecture because this material is a little bit difficult and you might not appreciate it on first lecture, but in the appendix to Rudin's first chapter, you have a rigorous development in terms of Dedekind cuts. So you can define real numbers in the following way. So you can think that R is a set that contains a bunch of elements that are elements of that are subsets of Q. Notice not elements of Q but subsets of Q, such that the following properties hold. First property is that alpha is not equal to Q. So it's not the entire rational numbers, and I might also say that alpha is not the empty set. Second property is that if a rational number in Q is in alpha, then any t belonging to Q such that t is smaller than R is in alpha. Okay? In other words, if you contain some rational number in this subset alpha, all the other rational numbers are going to be smaller. All the rational numbers that are smaller than this one are inside. And the third property, they might not be listed in the same way in Rudin, but the third property is that there is no biggest element in alpha. In other words, what this means is that R belonging to alpha implies there exists an S bigger than R which also belongs to alpha. Now this looks like a very, very complicated description. What is this and how is it related to real numbers and why is it a good idea? So I suppose the Aztecs, when they first saw a ship coming to the Americas, they did not understand what ship is, right, what a ship is. So they had to have a language for it. So they call it a floating rock. So this is a description of a floating rock. What this describes, in essence, it describes you can think of this as the number line, a little bit of cheating. And let's say I think of the number 1/2. Okay? So 1/2 will be made into a set, so you can make the set 1/2, maybe something like this. Will be the set of all r smaller than 1/2, where r is an element of Q. In other words, those are the half-open intervals. You see, so in other words, 1/2, what is this thing? This is just minus infinity to 1/2. That's how Dedekind describes the embedding of the number 1/2 into the real numbers. Now, you can by doing this procedure, you can actually create a comparison, an order, because you can now say, for example, that well, you can say that in general that alpha is smaller than beta if alpha is a subset of beta, right? Because, in other words, you can say that the set 1/2 is smaller than the set 1, right? Because this set 1 contains all rationals, including 1/2, that are lower than 1. This one only contains rationals lower than 1/2. Okay, so this creates basically an embedding of the irrational numbers. You leave them into another structure. Now, once you have sets, what you are able to do is you're able to take unions of sets, and taking unions of sets allows you to create a supremum. So the supremum would work something like this. So if you have a set A, and a set A now is a collection of a bunch of alphas, right? Where alphas satisfy this abstract definition of R that we have there. And it's bounded above means that there's going to be, it's bounded above if there exists a beta such that all the alphas are smaller or equal to beta. In other words, all of them are subsets, right? If there exists a half-open ray that is bigger than all the half-open rays contained in it. Okay, so I'm still making sense, I hope, a little bit, right? So all we do is we can construct a set of comparison, and the way to construct the sets is we only use rational numbers, and the rational numbers are easily seen, how they are they satisfy this definition. Other non-rational numbers, it's not quite easy to see how they satisfy the definition and what they are. But what we have is anything bigger than 1/2 will be a ray that is just extending more to the right. So if you have this, what do you think is going to be the supremum? So what is the supremum of A? Can anybody guess? You understand what happens here? So you have a collection of rays, all of them rays that are half open to the right, and all those rays are contained in some big ray. All of them are smaller than some big ray. So imagine, in other words, maybe the big ray is up to here, and I have a bunch of them that no ray extends over where I placed my palm. So what is supremum A? How would you calculate it? What can you do? Yes, please.
If alpha can be anything in R, then isn't it infinity?
No, I said A. I didn't say what it is. This is, maybe you see this as giving a property. I'm just really saying alpha. Basically, A is a collection of those rays. Some collection of those rays that I found to be bounded above. Okay, so first let me make sure you see what means bounded above. I have a bunch of rays, and there is some ray beta that contains all the rays in A. They are all inside of it. Can you imagine this? So an example, let me just give you just this example. So let's say A is equal to pretty much the numbers R, such that R is a rational number, and R is less than 2. Okay? So what this set is, it's a set of, let's say, what sets are inside here? What sets are inside this A? Is minus infinity to 0, is it inside of the set?
Yes.
Yes. Right? Is minus infinity to 3 inside of the set? No. So minus infinity to 3, that's set. That's what I refer to as the beta. It's bigger than anything inside of A. Do you see that? There is a bigger rate. So my question is, so you have some set here, arbitrary set, and all you know about it is that there is an array that contains all the arrays in A. What's the supremum of A? How would I calculate it?
If it were a closed ray, starting...
They are always open rays. They are always open rays. By the definition, you see, that's why we say there is no biggest element. No biggest element makes it an open ray. You see, this description, you can remember it because you are an Aztec. You have never seen rays. You have to somehow talk about this without actually using this notation. It's meaningless, right? So, yes, please?
So the supremum of A is just the supremum of beta?
Well, beta, what's the supremum of beta? Beta is just an element. Supremum of beta is beta. I'm asking, how do I find, when I say the supremum, I'm asking, how do I find the smallest ray that still contains all the others? How do I find the smallest ray that contains all the others? Do you understand why we need to have open intervals? Notice that they are comparable. If you take any two rays, they are comparable, right? Because one will extend, let's say, to 1/2, the other one will either extend to a smaller value or to a bigger value. And I can only say that because I'm using rational numbers, right? I can represent this ray in terms of rational numbers. What the elements are in other cases, I don't know. What's the supremum?
Would the supremum be just any element, just one number? Is that what
The
you're saying?
supremum is one number bigger. Again, those are numbers. It's a weird way of making numbers. It's a number that is bigger than all the numbers in A.
So it'd be beta.
Beta is, yes, no, that's sorry. My apologies. Bigger and nothing smaller than it is ever bigger than all the elements in A. Supremum is the least upper bound. Beta is some upper bound. Can you guess how I find the supremum? No, it's my fault. Again, I splashed it on the board a little bit. I think you're bewildered.
So can what's the difference between A and R? Because they look like they would be exactly the same, right?
No, A is a collection of subsets.
The way that it's written there is almost like the same as the way R is written. Two columns over, right? So that, yeah.
No, but let me try to explain again. Okay? Do you all know the notation for power sets? Okay? You know what's a power set of Q, right? So what we have is we have that R is a subset of the power set of Q. I'm going to define the power set. I'll talk a little bit about it later. But you all know what's a power set from earlier courses. It's a set of all subsets of Q. Okay? Now, any element in R, so if I have alpha is an element in R, you can say alpha looks like something like this. So minus infinity to something like this. That's what this description makes it look like. Okay? That's what alpha looks like. It's basically subsets of Q that are basically, if you look at the elements of Q it contains, there is no biggest element of Q it contains. Yet there is an element of Q bigger than all the elements in here. And for any element of Q inside of this alpha, every element of any rational number that is smaller than it is contained in the ring. Okay, so they are rays. Now, if I have rays, I can compare them, right? So I can push a longer ray or a shorter ray. So this number is bigger than this number because as sets, one contains the other. Make sense? So this is alpha. So this is alpha, and this so let's say this I call this I call here as alpha, and this I call here as beta. Okay, they satisfy. If you look at those descriptions, they satisfy the description. Okay. Now, this set that is consisting of rays, I'm asking, consisting of things that are defined this way, does it have the least upper bound property? In other words, suppose I find a set A, so let A be a subset of R that is bounded above, that is non-empty and bounded above. So how would that subset look like? So if I draw pretend number line, what I'm really describing, so how does the subset look like? So there's going to be some element here. So this is some element alpha, let's say alpha 1. Then there is going to be maybe some element here, maybe you call it alpha 2. Maybe here something else, here something else. But what does it mean to be bounded above? It means that for all of them, all of the things that are inside of A, there is a ray that is bigger than them. There is going to be some beta that contains all of them. Okay? So that means that, so A is bounded above means that for any alpha in A, any ray that A contains, A is a subset of beta. Does it make sense? That's what when you use this notation, A is less than beta. Now, the $1 million question, if I had $1 million. What then, you agree that A is bounded above. What then is the supremum? How would I calculate the supremum?
By condition 2, wouldn't have to be the max today?
The what?
The maximum?
Well, A might not have a maximum. In other words, A might not have a bigger set. Maybe I go a little bit more, a little bit more, a little bit more. It might not have a maximum. If it had, yes. Yes, please.
I'm just guessing here. Like geometrically, wouldn't it be like beta minus alpha?
Well, we don't know what subtraction is. So beta minus alpha, what is that? Yes?
Wouldn't it be whatever point alpha's, well, I shouldn't say ending at because you said alpha has no largest value, but whatever that value is where you're correct.
So first of all, before you answer this question, picture what is it that you're trying to find and how would it look like? You're trying to find an element of R. How would that element of R look like? It would look like a half open ray. Half open ray. Yes? How would I find that half open ray?
The biggest alpha that contains all other alphas.
And
So
how would I
the-
find this? Look at them. Look at those alphas. Look what happens
Add all the
here. So you
alphas.
take this set and this set, and what do you do together?
Well, if R is a power set of Q, then doesn't it have a maximum? Doesn't it have everything?
No, R is a subset of the power set defined by this condition. Again, power set is extremely huge. It contains the empty set. The empty set is not part of R by this definition, right? The elements that R contains are sets that are not the entire Q, neither the empty set.
So are you saying that there's not a power set, a set in the power set that has a maximum? Doesn't there have to be?
Again, R is not the power set. You are confusing. R is not the power set.
It's power set minus condition 1?
R is quite significant. It looks much smaller. A lot of things are missing there. Notice what's missing? Very obviously the right-hand rays are missing. A bunch of patched segments are missing.
To get a bigger one, you keep taking the union of the
Here
smaller
you
sets.
go. You take the union. Wonderful. You take the union of all of them. Look at it. Alpha 2 and alpha 1. If I take union alpha 2, alpha 1, I get alpha 1 in this picture, okay? So the supremum very simply is the union of all the alphas. And then, of course, you can rigorously show that that would be a half-open ray. Again, you understand? Psychologically, you think half-open ray. Mathematically, there is no such thing. You have no idea what a half-open ray is, so you have this description. Okay, that description is precise, and it does not say take the number line, take anything from some number and go to the left to minus infinity. It doesn't use a language that it is not possible to use. Right? But that's the picture that allows you to understand what's happening. So the supremum of alpha, supremum of A, I'm sorry, is just the union of all alphas where alpha is an element of A. And you just verify that the union of all the alphas will be, in fact, an element of R. Okay? I will just mention how you do addition very briefly. I don't want to go through the proofs again. It's a little bit difficult. Okay? But basically, the fact that it has supremum, you see that this structure, whatever that structure is, as a set structure, it has the least upper bound property. Right? If you believe that this is a half-open ray, it has the least upper bound property. Yes? I'm getting to you guys. You're not entirely confused.
Yeah. Not entirely.
Not entirely.
90%.
Professor, but originally when you said that the real numbers were set alpha in a subset of rational numbers, aren't all rational numbers real numbers?
Yes, this way, but again, not quite. What you do is you create a rational number lookalike in this construction. So alpha, you see, the rational number was 1/2. Here, the 1/2 is converted to every rational number less than 1/2. And then when you define the field properties, you define addition, multiplication, you define all those properties, that new creature behaves just like 1/2 behaved in Q. You see, it has the same properties that 1/2 had in Q, but yet it has more things. It has the least upper bound property which Q lost. Okay? Don't worry, it's gonna be easier. Don't space out completely. So that's the supremum. You can define addition, multiplication, and you can make it into a field. And you do that. I'll just show you addition. You can say you can define alpha plus beta to be the set of all R plus S, such that R is an element of alpha and S is an element of beta. Okay? And you can verify, again, you have to verify that this structure satisfies conditions I through triple I, 1, 2, 3, that this is indeed, it looks like a half-open ring. So you can define multiplication, that's a little bit more tricky. You can define all the properties of fields. I hope you know a little bit about fields. But because this topic tends to be a little bit dense, what we do, we are just going to skip it. We are pretending that we completed this construction, and we're going to write the theorem. And the theorem is going to say theorem. There exists a field R that contains Q and R has the least upper bound property. You can do it using Dedekind cuts. I will give you a simpler description, one that you will understand maybe a little bit easily. But let's first see the consequences of this. This you can take as your axiom. or as your theorem, that's basically what you do with R. So there is this theorem that will prove. So if x and y belong to R and x is bigger than 0, there is a positive integer n such that n times x is bigger than y. This is known as Archimedean property. The Archimedean property n acts as a lever. Okay? So let's see why that is true. Actually, there is also a second condition that's going to be very important for us. If x and y belong to R, such that x is smaller than y, there is some R belonging to Q. There is a rational number such that x is less than R and R is less than y. So that will say that rational numbers are dense, they are very frequent. You can find, if you take any 2 points on the real number line, between those 2 points you have a rational number. Okay? So proof. So the first condition is we can consider the set, so x is smaller than, so if x is smaller than y, then consider the set A, which is going to be all possible integer products of n times x. So n is a natural number. If n times x is less than y, or less than or equal to y for all n. If it's going to be by contradiction that if n times x is less than y for all n, then A is bounded above. And if it's bounded above, we are in this R. So that implies that alpha equal to the supremum of A exists. So what can we then say? We can then say that if I take alpha and I subtract from alpha x, alpha minus x is going to be smaller than alpha. That's, you have to review all properties of ordered fields. They're mentioned in your textbook. I'm kind of really loose about it. In Rodin, it's really precise, every aspect of it. So you can just kind of use your basic intuition. Alpha minus x is less than alpha. So that implies that alpha minus x is not an upper bound. Of A. Which implies what? Which implies that there is going to be a number of the form n times, let's write like this. So A minus alpha minus x is going to be less than some number n times x. Or some integer n. But then what you can do, you can move the x across. And what does it imply? This implies that alpha is less than nx plus x, which equal to n plus 1 times x. Which now n plus 1 times x is still integer, so this is just an element of A. So that implies that alpha is not least upper bound. So that's a contradiction. So that's the proof of A. Now, B follows this way. So what you can do is we have that x is smaller than y. So what we have is that y minus x is bigger than 0. Okay? So y minus x is a number that is bigger than 0. And that means that if I multiply it by a large enough integer, I will get it to be bigger than 1. So by part A, there is an integer n such that 1 is less than n times y minus x. And that implies that if I look at the segment, this one is nx, this one is ny, that this segment is bigger than 1. So bigger than 1. Now you understand what the proof is doing, right? So if I have, what I do is I take the gap, I take the interval y minus x, that is a small interval. By the Archimedean property, multiplying it by n, I can make it large interval. Now if an interval is large, no matter where you place it on the number line, no matter where you place it on the number line, there will be an integer somewhere in between. It's larger than 1, you agree? So I can try putting this edge at an integer, then this is farther than an integer, there will be an integer here. Anywhere you move it, there will be an integer inside. So notice that there must be an integer m belonging to the set nx and y. And so we have that nx is smaller than m, smaller than ny, and now I divide everything by n, and I get x smaller than m over n, and smaller than y, so that means that here is our r. found R. Okay. So I hope, again, the first, it was also dangerous to show you Dedekind cons, but I hope you understood this. Okay, that by this procedure you can define an ordered field, right? So what you do is you take the rationals, and out of the rationals you create half-open rays. Half-open rays. Okay, so 1/2 becomes all rational numbers less than 1/2. 5 becomes all rational numbers less than 5, and then other things, whichever they are sets that I cannot speak of because I don't have notion of other numbers other than rationals. Are going to be sets where there is no largest rational number, and for any rational number in the set, all the others are there. Okay. Now I basically created out of numbers. I created sets. Okay. Now by set theoretic properties, you can see that all those rays. That's why I want the rays. They are always one is always bigger than the other, or they're equal. No other possibility exists that makes it an ordered set. Okay. And then, because of the properties of unions, if you union, you have to prove it. If you union such structures, if you union open rays, as described through properties 1 and 3, what you get is an open ray. So now you created an ordered set that has the least upper bound property. So you have that thing that Q did not have. Then there is still a lot of work of making it into a field. In other words, you have to define addition. You have to define zero. You have to define multiplication. And all stuff. So in the appendix, it's done. You can read it. Okay? And then you create the structure, which you still, it's very abstract. You still don't quite understand what it has, but it has least upper bound property. Now, and it's a field. And if you look at it, you will see that numbers that I can represent, like 1/2 and 1/4, if I multiply them, I will get 1/8. I will get an array that is everything smaller than 1/8, or rational number smaller than 1/8. So I do have the rational numbers embedded inside of the structure. They're simulated within that new mechanism. So you can take the theorem for granted. All R is just Q made complete, made to have the least upper bound property. And then we need to see that it has roots. That roots can now be calculated. Theorem, and that theorem is just going to say that if x is any number bigger than or equal to 0, then there is a unique positive number call it y, such that y to the power of n is equal to x. So that means the nth root of x exists. In other words, if you remember the first lecture, we tried taking root of 2, root of 5, and we could not calculate it. It did not exist in Q. But within this structure, so x bigger than 0, so of course I mean x belongs to R, so I don't forget to mention this. So if I consider R, roots are now going to be possible. Let's prove it. So the first thing we're going to do is we're going to define A to be the set of all numbers t in R such that t to the power of n is less than or equal to x. So I'm going to consider all numbers that if I raise them to the n power, I either get x or something smaller. let's consider in fact, so R plus, so let's consider only the positive numbers. Again, I'm cheating, forgive me about it, but what is R plus? All those things you need to verify the Dedekind cuts, the appendix. So we take R a little bit like pretty much like Q, all the points in Q, and somehow we exterminate the gaps by saying it has the least upper bound property. So we have the set. And then what we can do is we need to show that this set is bounded above. And we need to show that it's not empty. So first, A is not an empty set. How do I know? I can take T equal to, for example, X divided by 1 plus X. Okay? Now, then you can say that T is smaller than the minimum of X and 1. Do you agree? Just as numbers, if I remove 1 here, I divide by something smaller, and therefore I get x over x, that's 1. If I remove the x, so now it's x divided by 1, we have this property. So then what follows is that if I take t to the power of n, that is going to be smaller than t, which is smaller than the minimum of x and 1, which is less than or equal to x. So t is in the set. T belongs to A. So it's not empty. Second part is A is bounded above. So how do I know that? Well, what I can do is I can take S to equal x plus 1. So then what you have is that S is bigger than the maximum of x and 1, since x is positive. It's bigger than the maximum. Right? It's bigger than 1 because I can remove the x, and it's bigger than x because I can remove the 1. So then I can try seeing what happens if I take s to the n. S to the n is going to be bigger than s, which is bigger than max x and 1, and max x and 1 is bigger than or equal to x. So s is an upper bound. You see? S is an upper bound. Basically, because it's an ordered field, if you take anything bigger than s, you take it to the nth power, it's going to be bigger than this result. So now we're going to find the root. So what we do is we define y to be the supremum of the set A. And we're going to try to show that this y is our desired root. We need to show y to the n is x. So what we're going to do is, we know that this is the supremum. So we're going to do the following. For h bigger than, let's say h bigger than 0 but less than y, I'm going to see that y plus h is bigger than y, so y plus h not an upper bound. Of 8. On the other hand, what am I saying? Not least upper bound. I should say better, it's obvious that it's not least upper bound. I should say that y plus h, because it's y plus h to the n, will have to be bigger than x. Okay, because y is an upper bound, y plus h is another upper bound. So what's the upper bounds of the set A? The numbers whose power is bigger than x, whose nth power is bigger than x. So we have this, and we can look at y minus h, again something that is bigger than 0. This is not upper bound. Of 8. So that means that y minus h to the nth power is less than x. So what we have is we have a picture like this. So if I look here, this is y minus h. If I look here, this is y plus h. So y and the nth root of x, I will mark it with a question mark. I'm not sure it exists, right? So better I would say this. If you have y minus h to the n, and here is y plus h to the n, then y and x are somewhere. Y to the n and x are somewhere in between. And our goal is to show that the distance between y to the n and x is 0. Y to the n minus x and absolute value is equal to 0. Okay, so this is clear, right? Y minus h to the n smaller than y to the n. Yes, that's the order of numbers. If you multiply smaller numbers by themselves against bigger numbers by themselves, the product of the smaller numbers is smaller than the product of the bigger numbers. That can be done, of course, later. So here is how we're going to accomplish this goal. So we have that y to the n minus x is definitely less than or equal to y plus h to the n minus y minus h to the n. Yes? Now do you remember how you factor? Those are two numbers. This is like b to the n minus a to the n. Right? To make it simpler, let's think of this as b and this as a. And how do you factor the product of, or the difference of nth powers? This would be b minus a. I'll put actually on the bottom. This is b minus a, and here you would be having b to what power? N minus 1. Next it would be plus b to the n minus 2a, and so on and so forth until a to the n minus 1. So what is b minus a? b minus a will just be 2 times h. Do you see that? Y plus h minus y minus h is just 2 times h. So this becomes 2 times h. And what do we have in this product? Here we have y plus h to the power of n minus 1. Next is y plus h to the power of n minus 2 times y minus h. So on until you get to y minus h to the n minus 1 power. So we can simplify this. We only need inequality. So this is less than or equal to 2 times h. And then notice what I can do in parentheses. Y plus h, y is smaller, so h is smaller than y. Then y plus h is smaller than 2 times y. So I can write this as 2 times y to the power of n minus 1 and made it larger. Yes? This, I can, this is y minus h, I can replace it, make it bigger by y plus h. So this is also 2y to the n minus 1 power. This is inequality. You see what I do? Each part I replace by a bigger one. And the very last one I replace by just 2y to the n minus 1 power. So altogether, what do we have? We have 2 times h times how many such copies? N copies, right? So times n to y to the n minus 1 power. And what is this? This is then 2 to the power of n times y to the power times n times y to the power of n minus 1 times h. Aha! And h I can make as small as I like. So you see this? So here what we're going to do is we're going to say that this is less than epsilon for any positive number. So here what you do is you take h to be smaller than epsilon divided by 2 to the n and y to the n minus 1. Okay. So what's the conclusion? The conclusion is that y to the n minus x is smaller than any positive number. Right, this epsilon is arbitrary, so it's smaller than any positive number, and the implication is that y to the n is equal to x. So let's look at some corollaries. I should, by the way, remark, it's obvious that y is unique. Y is unique because if z is, let's say if z is less than y, then z to the n is going to be less than y to the n, which is equal to x. And if z is bigger than y, if you take a bigger number than y, then you have that y to the n less than z to the n, and this is equal to x. Okay? So uniqueness is obvious as long as you understand that it's an ordered field, two words that are important. So now we can mention the corollary. So if A and B are positive, real numbers, and n is a natural number, then we can define the nth root of AB, and that would be equal to a to the power of 1 over n times b to the power of 1 over n. And the reason for that is very simple. You can just take alpha equal to a to the 1 over n, it exists, it's unique. And you can say beta equals to b to the 1 over n, it exists, it's unique. So then if you take alpha times beta to the power of n, it ends up being alpha to the n times beta to the n, which is a times b. And by uniqueness that must hold. Okay, this notation, again, I'm glossing over it. This notation makes sense only because solutions are unique. It's not at all so with complex numbers. Let me just remind you for a moment. Let's say in real numbers, recall, so if I take 1 as an element of the real numbers, then I can consider what is 1 to the power of 1/3. In other words, what number that multiplied by itself 3 times will give you 1. And you will say the answer is 1. But if let's say you consider 1 as an element of the complex numbers, right, where you are allowed to use imaginary numbers, then you can look at 1 to the power of 1/3. It will equal several things, right? It will equal, on one hand, if you don't know, don't worry, right? I'm just showing you what can happen. So that can equal 1, just like before. It can equal to e to the I 2 pi over 3, which is cosine of 2 pi over 3 plus I sine 2 pi over 3, which equals to, this equals to minus, what is it, I'll keep it like that, I'm not really able to think at all today. So, and the other possibility is e to the I 4 pi over 3, and that equals to cosine of 4 pi over 3 plus I sine 4 pi over 3. Okay, so it will have 3 solutions. Okay, and if you take fifth power, it will have 5 solutions. That's because the complex numbers are not an ordered field. You cannot make them an ordered field. That's one of your exercises. But again, you can ignore this is just a side step, right? This notation makes sense because there is going to be a unique solution in the field of real numbers. So all of it, I'm assuming, was enormously confusing. Right? So you came here not knowing what real numbers are, and you are about to leave knowing even less. Right? And that's all thanks to me. So let me give you a description that makes a little bit more intuitive sense. Right? We said, what are rational numbers? Rational numbers can be thought of as fractions. Correct? And what are fractions? Fractions is just also a finite addition of them. Right? So let's say 5 divided by 2, it's just 1/2 added 5 times to itself. And any other fraction can be considered as a finite sum of fractions. Okay? Now, using this idea, I can try to describe what real numbers are. And we're going to do that by the following theorem. Very important proposition which we will use. So, do you mind if I erase this here? So, what are real numbers?
What's irrelevant?
So, proposition. So, fix an integer p bigger than or equal to 2, and let the sequence a sub n be any sequence of integers such that 0 is the smallest it can be. So an has to be 0 or more. And the biggest it can be is the integer p minus 1. Okay? And that's true for all n. Then the infinite sum n equal 1 to infinity a sub n over p to the n converges to a number in 0, 1. Okay, that's the first proposition. So the proof, it's pretty simple. You can just look at the summation, so look at the sum. So it's a positive sum, and it is bounded above by this sum. So if I increase all the a sub n and I make them p minus 1, then I create a bigger sum. And well, clearly this sum is it's bigger than or equal to 0, and this is less than or equal to this sum. And what is this sum? This is simply 1. Okay, this is simply 1. Do you remember how to calculate power series? Sorry, how to calculate geometric series? If not, I will go over that maybe next class. So that tells you that this number, whatever this summation x is, this number is between 0 and 1. So now the more interesting theorem or proposition and that would be that any x in the interval 0, 1 can be represented this way. By the sum So here is a proof. So what you have is you start with a1 divided by p, such that the product here is less than x. Well, basically we can assume that x is bigger than 0, because to create 0 you just set all the an's equal to 0. So you can say that so x is just some number bigger than 0. We have that a1 divided by p is going to be less than x, and it's the largest one less than x. In other words, a1 plus 1 over p will be already bigger than or equal to x. So you can ensure that by the Archimedean property. Think about it, right? So we take 1 over p. 1 over p is a positive number. I either multiply it by 0 or by 1 or by 2. Right? Definitely I don't need to multiply it by p, because x is less than or equal to 1. So a1 never has to exceed p. Make sense? So I can make this condition true. Now once I have this condition, I can now define a2. So basically look at a1. a1 is 0, and at most it is p minus 1. Now I can go to step 2, so I can have a1 over p, and I add to it a2 over p squared. This a2 I'm going to increase from 0 all the way until I get p minus 1. So this I'm going to increase so that it's never exceeding x, right? So I'm going to make a2 0 if necessary. If not, I try to make it 1 and see if it's still less. And if not, I make it 2 and see if the sum is less. And the sum is supposed to be less than a1 over p plus a2 plus 1 over p squared. Now here again we have that a2 is bigger than or equal to 0. That's clear, right? Either I add 1 over p squared, and I can still add more, or if I add 1 over p squared and I'm bigger than x, then I put a2 equal to 0. So a2 is bigger than or equal to 0, and this other part might be less clear. It's less than or equal to p minus 1. Why is it less than or equal to p minus 1? Think what happens, right? If it is equal to p, if I need to go with a2 as far as I go to p. Can you see? Imagine a2 is p. I'll do it here. So if a2 equals p, or if a2 is bigger than or equal to p, and then we have that a1 over p plus a2 over p squared is bigger than or equal to a1 over p plus p over p squared, which is equal to a1 plus 1 divided by p, which is bigger than x. So by the previous step, I cannot make a2 go beyond p minus 1. And continuing in this way, you eventually arrive at a1 over p plus a n over p to the n less than x, and x is less than or equal to a1 over p, plus all the way to an plus 1 over p to the n. Okay? And this way I construct an infinite sum that is always less than x. Continuing in this fashion will produce the desired result. Notice that here the amount of error is 1 over p to the n. Each step, the amount of error is at most 1 over p to the n. So before you leave, just one brief phrase then, what are real numbers? Rational numbers were finite sum of fractions. Now I can construct every number from 0 to 1 as a sum of infinitely many fractions. Okay, so if you allow the summation of fractions to go to infinity, you can construct all the real numbers between 0 and 1, and by adding the appropriate integer, you can slide the interval 0, 1 anywhere, so you can create any real number. Okay, so real numbers are just infinite sums of fractions. Right, have a good one.